Welcome to CCAI321 Artificial Neural Networks. Previously, we learned about multi-layer perceptron, looked at a number of classification example problems, the use of multi-layer perceptrons for function approximation, the backpropagation algorithm, and batch versus incremental training, and using the backpropagation algorithm, followed by several examples. In this section, we will study convolutional neural networks, or CNNs. We'll do an introduction to CNNs, introduction to the operation of convolution, why we use convolution, convolutional neural networks, and operations that are frequently used in convolutional neural networks, meaning zero padding and pooling, and in the end, some practical examples of using convolutional neural networks using the MNIST Python library, and some examples of CNN architectures in the real world. Convolutional neural networks, or CNNs, are also called ConvNets. It's an abbreviation that you will frequently find. What neural networks, these are basically neural networks that process data using a grid-like topology, and we'll get to see that in image form quite a bit in this section. Now, convolutional neural networks are quite successful in processing one-dimensional data, such as speech, and also two-dimensional data, such as images. The name these CNNs get comes from the convolution operator that you may be familiar with from a course in signals and systems. CNNs use the convolution operator for the purpose of feature extraction from inputs. Practically, these neural networks that are also quite deep in the sense that up to this point, the multi-layer perceptrons we saw went up to 3 layers. So by the end of this section, you'll see networks with more than that, 5 to even 7 layers. And of course, deep neural networks can have many layers more than that even. So let's look at the convolution operation first of all, how it is performed, and what performing that operation in a neural network would mean for us. This is a mathematical representation of convolution. Now, we have over here two functions, f and g, and this is, I should add, this is just one-dimensional convolution. So to give you an idea on what happens in 2D, but we have two functions over here, f and g. So f is this represented here by these sequence of 6 non-zero values in this blue-purple box, and function g is this much shorter function with only 3 non-zero values, 1, 2, and 3. So mathematically, this is how one-dimensional convolution is represented. Now, this may not mean much to you, and that's why we will look at convolution and its graphical representation right from the beginning. On the left-hand side of this equation, you'll see the star operator. That's not multiplication in the sense that it is used in many programming languages. This is not supposed to be multiplication. This is actually an asterisk, and it represents the convolution operation, just like we have the plus, minus, multiplication, and division symbols. The asterisk represents the convolution operation here. And so here at the bottom of this slide, you'll see only the first 4 steps of finding the first 4 values that you get from the convolution operation. So the first value is obtained like this. You take function g, so you keep one function in its place, let that be function f, and then you keep the other function g, put it underneath it over here, and you slide it to the left, and then you bring it back to the right until the first field, the first non-zero value of function g overlaps with the first non-zero value of function f. So that would be the values 3 and 1 in this case. And what we do is we basically multiply these overlapping values. And in this case, there's only one position in which values of the function f and function g are overlapping, meaning they're like one on top of the other. So we just multiply the two together, and the answer is 3, of course, and that is what you see over here. That is the first output value from the convolution operation. Next, we move function g one more step to the right. Now we have 2 positions in which values of function g and function f overlap. So the 1 and 2 on the left and the 3 and 2 on the right. So again, we multiply overlapping values and add up the results. I'd add up the product. So 1 multiplied by 2 plus 2 multiplied by 3, in this case, gives us 8. And 8 is then the second value returned by the convolution operator. So the input to a convolution operation are 2 functions, and the output is also a function. Next, we move the function g one more step to the right. Now, all 3 non-zero values of function g overlap with some values of function f. We multiply the overlapping values and add up the results, and we get 1 times 1 plus 2 times 2 plus 3 times 3 in this case. Add all of these up, you get 14. And 14 is the third value that you see over here. And just to continue with this, fourth step would be moving the function g one more step to the right. Now we have 1 and 2, 2 and 3, 3 and 4 overlapping. Compute these products, add them up, and you get 1 times 2 plus 2 times 3 plus 3 times 4 equal to 20, and that is the fourth value of the convolution function. And if you continue this all the way until you have the function g over here, until function g completely escapes and has no more overlapping value with function f. And if you do that, you get this function that you have over here, you get that at the output. The length of the convolution product, that's what this is also called, length of the convolution product will be the length of function f plus the length of function g minus 1. So let's see, the length of function f is 6. We have 6 values over here. Length of function g is 3. We have 3 values over here. So then the length of the output must be 6 plus 3 minus 1, which is equal to 8. You can see we have 1, 2, 3, 4, 5, 6, 7, and 8 values over here. And this is convolution for one-dimensional signals. This is what that operation looks like. Now, convolution can also be performed for two-dimensional signals, or think of them as images here. So for two dimensions, we have some sort of input image. Consider this as a grayscale image, not a color image. So just a picture in which pixels are varying shades between black and white with different shades of gray in between. You can have a two-dimensional filter, typically square shaped. In image processing, these are typically square shaped, and they're also typically symmetrical. I'll show you what I mean by that. And the output is of performing convolution between these two is what we call a feature map. So I'll show you in image form what convolution means in two dimensions. So begin like this. So this dark red area that you see over here, that is the filter. You align it with the you align its top left corner with the top left corner of the image, the input image, and you put them one on top of the other, and you perform a multiplication of values in overlapping boxes. So that would be 9 multiplication operations over here, because the filter itself is 3 by 3 in size, meaning it has 3 rows and 3 columns. So we have 9, we perform 9 multiplication operations, and we add up the products that we get from those 9 operations. That is WT times X, that's equivalent to this operation. The weights over here, the values that you see in the filter are basically the weights. X are the input values from this input image that you see in blue over here. When you add them all up, you get one number. That number is what you see here represented by this black dot in this image. And that is the first input. The first output. Then, for the next step, you move the filter one field to the right, and you redo the same operation, perform multiplications of overlapping fields, overlapping values, add up those 9 products, and you get one number. And that number is the second value in the output. Guess what? This is step 2. What is step 4? Step 4, the filter will be all the way at the end of the row, and we will have performed the same multiplication, 9 multiplication operations, followed by addition of all the products that we get, and that will get us the 4th output. And what next? What comes after that? It's at the end? No. It's still the lower half of the image that hasn't been touched at all. And so what we do is we move back to the beginning for step 5, we move back to the beginning of the column, back to column 1, but we also move the filter down by 1 position, by 1 step, and repeat. And that will be step 5. And then move the filter again 1 location to the right, and that will be step 6. And you continue this for step 7, for step 8, for step 9, for step 10, for step 11, 12, 13, 14, 15, all the way to the last step, 16, by which time, in this example, the filter will have reached the last column and last row over here. And again, compute the last output value from this 2-dimensional convolution operation, and that will complete the output image, or the convolution product, two-dimensional convolutional operation of this two-dimensional filter of size 3 by 3 with this two-dimensional input of dimension 6 by 6. Now in this example, we moved the filter, also called the kernel function. Also, we moved that one step at a time. We only moved the filter ahead by one step. That one step does not necessarily have to be one step, and the proper term for that is stride or step size. So the stride that we used for this filter was 1. We moved the filter ahead by one location at a time. Now, it's not necessary that that stride always be only one step. You can make it 2, you can make it 3, and I'll show you some examples of what that does. Now, given that we have over here a filter of size 3 by 3 and an input image of size 6 by 6, and the stride that we used was 1. We can actually figure out the output, the size of the output image or the feature map. We can figure that out by this simple expression, n minus k divided by s plus 1. That is the dimension of the output feature map for an input image that has size n in that same dimension, is being convolved with a filter of size k along the same dimension, moving with the stride s. So in this particular example, the dimensions, the horizontal and vertical dimensions of the input image and the filter are both the same. So it's 6 by 6, it's a square shape, and the filter is 3 by 3, also square. So you can consider this, so this holds true in this case. The output size will be the same for along horizontal and vertical direction, will be the same for the feature map as well. So in this case, the input n is equal to 6, filter size k is equal to 3 along both dimensions. The stride size was 1, and if you put in those numbers, so 6 minus 3 divided by 1 plus 1, 1 is a constant, that gives you 3 divided by 1 plus 1 equal to 4. So the output size of the output image will be 4 along both dimensions. And you can see that over here that is actually true. Now, if you want to see the calculations that are happening, if you want to see them slightly more explicitly, there's another graphic or another image that shows that. So we start out with this yellow colored 2 by 2 filter in this case, a kernel. The 4 values in that kernel are W, X, Y, and Z. And we have an input image over here of size 4 by 3. Kernel of filter size is 2 by 2. Stride size is 1. So just before we begin, so along the horizontal direction, that means 4 minus 2 divided by 1 plus 1. So the size of the output image will be 2 plus 1 equal to 3 along the horizontal dimension, and you can see that is true. And along the vertical direction, it's 3 minus 2 divided by 1 plus 1. So 2. You can see it's 2. So each of these boxes down here represents one of the values of the output image. And what this figure shows is that in order to compute the value of the first pixel, in the upper left corner of the output image, what we do is we multiply A by W, B by X, E by Y, and F by Z. That's these 4 values over here, and we add them all up. And that's what gets you the value in this upper left pixel of the output image. What happens next? You move the filter one position, one step to the right, and you perform the of operation B times W plus C times X plus F times Y plus G times Z. And that gets you the value of the pixel in the second column, first row, second column. Then you move the filter one more location to the right, and that gets you that'll get you the pixel value in row 1, column 3, and that will be C times W, D times X, G times Y, plus H times Z. That's what we see down here. And that gets us to the end of that, to the end of the image along the horizontal direction. And so the next step will be to move the filter back to the left, the first column, and down by one step. And the value of the pixel in the second row, first column, will be E times W plus F times X plus I times Y plus J times Z. That's what you have over here. And so on. You can do the same thing for the last 2 remaining pixels. So that's basically it. That's how 2D convolution works. Now, depending on the values in the filter that you have, you can accomplish different tasks. So, for example, if you can use an edge detection filter, something that looks like this. You have these negative values in one column, you have 0 values in the middle column, and you have positive values in the right column. And this is a filter that will help you detect vertical edges. And then we have another filter over here for horizontal edges, so horizontal lines. And this one contains positive values in the top row, 0 values in the second row, and negative values in the third row. Typically, another thing that is true for filters in image processing in particular is that the total sum of all the weights in a filter, they're often normalized to in such a way that they sum up to 0. So if you add up all of the -1 and +1 kind of cancel out, -2 and +2 cancel out, -1 and +1, and this of course is the column of all zeros. So the sum total of all the values in this filter GX is 0. And the same thing for this other filter GY. +1 cancels with -1, +2, -2, +1, -1, with the middle row being all zeros. So these are filters that can be used for edge detection. These particular ones, they have a name. They're called Sobel filters. And if used on an image, like this one over here of a butterfly on the left, it can give you as output an image that you see over here on the right. Another action, another operation that you can perform with the filter is uh, uh, you can use it as a low pass filter. You can use it to blur an image, and it's a very simple filter for that. Like this one over here. So basically all ones over here. I know in this particular case, all the values do not add up to one, which can be to zero, which can be problematic. It can lead to um, saturation. So usually in this case, you would do something like 1 by 9, 1 by 9, because you have 9 different values in this filter. 1 by 9, 1 by 9, 1 by 9, just to make sure that you would get a saturated image, something that's way too bright or just all white in places. So if you use this low pass filter, this blurring filter on this input image on the left, you get the image here on the right. You can see it's definitely a much blurred version of the input image. So why talk about convolution at all? Why do convolution at all? What's the advantage of using convolution? The advantage is that convolution operations, or a layer that performs convolution in a neural network, will have a much smaller number of parameters that have to be trained. So they're much. So remember, if you have, as in this case over here, you have um, 4 inputs, 5 outputs, and this is in a fully connected layer. So layers, the kind we've been dealing with up to this point, in which every input connects to every neuron, and this is the number of connections that you see over here. Each connection over here is associated with, or has associated with it, one parameter. That's a lot of parameters for just 4 inputs. On the other hand, on the left side, you can see a convolutional layer in which not every input connects to every neuron or to every output. And you can clearly see that over here on the right, we have many fewer connections, meaning many fewer parameters to train. And as you now know from the backpropagation algorithm, the more neurons you have, the more parameters you have to train, the more weights, the more biases, but primarily the more weights. Um, the more times you have to run the backpropagation algorithm every time. Fewer parameters means fewer weights to train, means faster training. And recall that this is still a very simple example of just 4 inputs. Images that you've seen, they can have dimensions. I mean, if you have a decent sized image, it can easily be like 1,000 pixels by 1,000 pixels, and you can see very quickly that the number of parameters that you'd have to train for a fully connected network that takes such a large image as input can be quite prohibitive. So convolutional layers basically make the interactions between inputs and neurons it sparsifies them. So you have many fewer connections, many fewer parameters to estimate. So if you have, for example, m inputs in a layer with n neurons, you'd have to find m times n weight parameters. If, on the other hand, uh, each neuron is limited to only k connections, where k is much less than the number of inputs, you'd have only k by n parameters. K, of course, assuming is much less than the total number of inputs to that layer. An image, a small image, I should say, you can visualize it, is often visualized like this. So this over here represents a very small 32 pixel by 32 pixel image. It's not much. On top of that, color images consist of three color planes, red, green, and blue, which means not only do these images have width and height, they also have a third dimension that we call depth. So that would be, for an input image, typically that would be 3. A single filter can be usually much smaller than the image size itself. So you could have a filter like this, size 5 by 5. But because the image that you're dealing with has depth, the filter must also have depth. And that depth of the filter has to match the depth of the input image. Now, you're already familiar with how the filter slides over the input image. Now, just because we have a third dimension does not mean we slide the filter in 3 dimensions. Instead, the filter remains fixed in the third dimension. So 3 values along the depth axis always overlap with the same, with 3 values in the depth dimension of the image. So the filter does not come out of the image at any point, at any time. So over here, this is how you can think of an image of size 32 by 32 and depth 3 being convolved with a filter W of dimensions 5 by 5 by 3. The end result in this case will still be a single number. So in this case, we'd be performing for each output number, you'd be performing 5 times 5 multiplications times 3 because you have 3 layers, and then this is, in this case, it's 120, that's 25 times 3, 75 multiplications, so 75 products, and then you'd be adding them all up, and that's what gets you this one pixel value of the output, one output value of one output value of the filter. This operation is, and there's of course adding the bias value, so about 75 additions after that, summation operations after that. This operation is equivalent to this one over here, W transpose X plus B. Once you've slid the filter over the entire, all valid positions of the input image, you will get an output image, and that will be of these dimensions. It'll be 28 by 28 of height and width, 28 by 28, but will have a depth of only 1. Why 28 by 28? Well, remember 32, so n minus k divided by s plus 1. That's the size of the output image in any dimension. So both dimensions over here for the filter and image, they're both square shaped. So 32 minus 5, stride size 1 plus 1, and that gets me 27 divided by 1 plus 1, or 28. So that's why the output image is 28 by 28 in size. Now what you can do with one filter, you could easily apply a second filter to that same input image. So you can use multiple filters in the same layer to the same input. So if you apply a second filter, this one is shown in green, usually of the same dimensions. So the first one in this layer was of size 5 by 5 by 3, the second filter will usually share the same dimensions, so also 5 by 5 by 3 in this case, and will produce this green output image in this case, also of the same size, 28 by 28 by 1. And you can easily imagine that you can have many such filters in a single layer. And for example, we'll see some examples of in which we use many filters in the same layer. In this example over here, we have used 6 different filters, giving us 6 different images of sort at the output. 6 different feature maps, I should say, at the output. Each of the same dimension, 28 by 28. Now, this is what can happen in what you can do in one layer. And remember, you can have multiple layers in a neural network, which means you can have in one layer, you may be applying a 5 by 5 by 3 filter. You may be going, just like we just did, from a 32 by 32 by 3 image, you'll be going to a 28 by 28 by 6 output. And in between, you'll also have some activation function. So what we just did, that was the convolution part of a convolution layer that can, of course, be coupled with an activation function, something we haven't talked about yet. So a ReLU function, for example, something that's commonly used in convolutional neural networks. Then going to the next layer, you may want to perform convolution again, this time with filters of size 5 by 5 by 6. And notice that we have the 6 over here. It has to be 6 because the input to this layer will have depth 6. So filter depth has to match the depth of the input volume or image. Sometimes we also call this an input volume because we look at it in 3 dimensions. We consider it as 3-dimensional data. So we perform convolution with a 5 by 5 by 6 filter over here, and we've got, let's say, 10 of rows, and followed by the use of the ReLU function for the activation function. And the output from that will be an output image of size 24 by 24 by 10, because we're using 10 filters over here. And so on. You can keep doing that. You can perform convolution followed by an activation function. And this is how the dimensions of the output of one convolution layer determine, or partially constrain at least, what the dimensions of the filter of the next layer must be. And of course, over here you'll also notice that the dimensions, the height and width dimensions, seem to be reducing with every step. So we started off with a 32 by 32 input image. That became a 28 by 28 volume, and was further reduced to a 24 by 24 volume in the third step, and so on. So we'll talk about that, how to deal with this steady reduction in the output sizes, in successive output sizes of successive layers. But before we do that, let's talk about another issue. So the stride sizes. So far we've always assumed that the stride is 1. But what does it look like when we choose stride 2 or stride 3? Can we pick any value for the stride? Let's assume we have this image of size 7 by 7. And we want to apply a filter of size 3 by 3 to it with a stride of 1. It seems pretty straightforward. This will be the starting position of the filter with respect to the image. And you can find the next value repositioning the filter one step to the right, another step to the right, another step to the right, another step to the right. So there's not much of a problem that you see over here. Then we move one row down and repeat the same thing all the way to the end until we land with the filter in this position over here. So the output image from applying this filter over here will be of dimension of size 5 by 5. Now let's try something different. Let's try the same image, the same filter size, but a stride 2. This means that we start out at the same position, but for the next output value, we move the filter 2 positions to the right. That puts it right over here. And when we're done with that, we move it another 2 positions to the right, and that gets us to the end of the row. The output image, you can see 3 steps got us from the left side of the image to the right side. 3 steps, which means the output image will be size 3 rows, and because both filter and image are square shaped, also 3 columns in the output. The next position for the filter after this will be over here, then over here, then over here, followed by this position, and finally this position, giving us a 3 by 3 output. So 2 steps right every time, and 2 steps down, 2 fields down when we reach the end of the row. What about stride size 3? So again, we have the same starting position. You move, for the second output, you move the filter 1 position to the right. You land at this position, but you can easily see a problem now. We have never gotten to this column over here, the last column, and we never will, because it is not possible for us to move the filter another 3 positions to the right, because we would be overrunning the size of the image. So, since the edge of the image can't be reached, this edge over here, the edge of the image cannot be reached, and we'll face the same problem in the other dimension. Since the edge cannot be reached, we cannot apply a 3 by 3 filter with stride 3 to a 7 by 7 input image. Now, instead of having to try this out and see if the filter fits the image, what we can instead do is we can use the formula that we have to compute the output dimensions of the output image. And in this case, when we used stride of 1, that meant 7, meaning n, minus 3, that's the filter size, and stride 1, 7 minus 3 divided by 1, plus 1, which got us an integer value of 5. When we use a stride of 2, that becomes 7 minus 3 divided by 2 plus 1, which still gets us an integer value 3. And so the output images from stride size 1 was 5 by 5. The output image from stride 2 was 3 by 3. But see what happens when we set stride s equal to 3. 7 minus 3 divided by 3 plus 1 is 2.33, and there cannot be any fractional images. Images cannot be of fractional pixel sizes. So if you get a fractional number over here in the output, for the output image size, means that that filter cannot be used with this particularly sized image. So what's a solution to this? A solution to this is something called zero padding. You can add pixels. You can add a frame of 0 pixels around the image that you're trying to process. So, for example, over here, you could add 2 rows and 2 columns of all zeros to an existing image. And not only that, not only can you use zero padding to resize an image so that you can use a particular filter with a particular stride, you can also use zero padding to make sure that the output image from a filtering operation does not grow too small. So basically you can grow the size of the image before input and then apply the filtering operation to it. So for a filter of size k and stride 1, the number of zeros that you should be using is k minus 1 divided by 2. Let me give you another bigger example. So let's say we have in order to retain the same output image. So let's say you have an image of size 32 by 32, a filter of size 5 by 5, and stride 1. Now, ordinarily, the resultant image would be of dimension n minus k divided by s plus 1, which is 32 minus 5 plus 1, or 28, which are the same dimensions. Not the same dimensions, but it's a reduction of so the image started out as a 32 by 32 image and ended up being a 28 by 28 image. Now, if we let's see, if we use this formula over here, k is equal to 5, stride size is 1, so k minus s divided by 2, then you get the answer 2 over here. So if you add 2 pixels on the left side of the image, and if you add 2 pixels on the right edge, the right side of the image, kind of like here, and you've extended the image by 2 pixels on the left, and by 2 pixels on the right. Now, what you do for one dimension, you can do for the other dimension. You can extend the image by 2 pixels on the top and 2 pixels on the bottom. And you can clearly see, just complete these corners so you have something square shaped. This is how you pad enough zeros to make sure that the output image does not stays the same in size as the input image, as long as stride is equal to 1 in this this case. Now you can use, like you just saw, you can use multiple filters in each layer, and each filter can be used to extract different types of features. So, for example, you could have something like this as an input image, and you can use different filters to produce different feature maps for the output. So if you have 100 filters, you get 100 feature maps. Basically maps showing where a certain feature captured by the filter, where is found, in which position, which places of the image that particular feature is found. So assume that you have an input image of size 28 by 28 by 3. So simple RGB image with equal width and height, 28 pixels, 3 color channels. And let's assume we want to pass it through, well, the filter can have any width and height. In this case, it has width and height 5, but must have matching depth of 3. So 5 by 5 times 3. And let's say we select a stride of 1. And we don't have only one filter, we have 100 filters. Question: what is the number of parameters that you have to learn for this layer? Well, it's quite easy. 5 by 5, that's the number of weights that you have to learn for the filter, times 3, because it has a depth of 3, plus 1, an additional parameter for the bias. That's 76 in all, and if you have 100 such filters, it makes for 76 times 100, or 7,600 parameters. If this seems like a lot to you, go back to the size of the image. Assume that you have a fully connected layer, and see what the number of parameters would be for that. It makes for a good exercise. Okay. So convolutions generally replace the part of the neural network that usually gave you the n values, the n vector in a neural network. And that is then followed up by a transfer function that gives you the final output value A. In the context of convolutional neural networks, these two steps of computing these n values and the A values. These are separate, usually oftentimes referred to as separate layers. So we call that a convolutional layer followed by some activation function layer, like a ReLU layer. The non-linearity of the neural networks is attributed to the use of a non-linear activation function, like the ReLU function. Now, as you go along, as you go through layers, you can reduce the size of the, you reduce the number of parameters that you're dealing with by using something called a pooling layer. So, and that is basically a deliberate reduction of the size of the image. I'll talk about that briefly. So, say an image has a size 32 by 32 by 3, color image of size 32 by 32, filter of size 10, and there are 10 such filters. The filters use stride 1. So n is 32, k is 5, s is 1. Which means, what is the size of the output? The size of the output will be and minus k divided by s plus 1, same old, same old. So 32 minus 5 divided by 1 plus 1 for the bias. Not for the bias, I'm sorry. So 32 minus 5 divided 1 plus 1 gets us 28. Now, since it's a square image again, that makes the height and width of the image 28 by 28, and because we're dealing with not one but 10 filters, remember, that makes the size of the output 28 by 28 by 10. Now, if we zero pad the input image with 2 pixels, what will be the size of the output? And when I say 2 pixels, I mean 2 pixels above, 2 pixels below, 2 pixels to the left, 2 pixels to the right. Well, in that case, the size of the input has changed to 28 plus the left padding plus the right padding, which is 28 plus 2, or 28 plus 4, or 32. So the size of the output, if you want to recompute that, will be 32 by 32 by 10 if you use this padding. And what is the number of parameters in the layer? That depends on the filter and the number of filters that we have. Dimensions of the filter are 5 by 5 by 3, depth is fixed, plus 1 for the bias. Yes, that's for the bias over this one. It's a 76. And because we have 10 filters, it makes about 760 parameters. And here's an example that shows you what a convolutional neural network solution looks like from end to end. So this here represents a convolutional neural network approach to a classifier that classifies apparently between a car, truck, airplane, ship, and horse. This over here, this nice looking Tesla represents the input image, input image, and each column that you see represents one layer of a neural network. What type of layer? That's what it's given here at the top. So the first layer is a convolutional layer, followed by a ReLU layer. Another convolutional layer, followed by a ReLU layer, followed by something called a pool layer that I'll talk about next, followed by a convolutional ReLU layer, convolutional and ReLU layer, followed by another pool layer. Convolutional and ReLU layer, convolutional and ReLU layer, followed by a final pool layer, which is then used to determine what this image most likely is: car, truck, airplane, ship, or horse. And that's where you see this histogram over here, basically representing the confidence values with which this neural network thinks, or the probability values this convolutional neural network assigns to the different output classes, possibility with which this input belongs to a certain class. So, the pooling layer, the name appeared once before, still haven't talked about it. So, the purpose of a pooling layer is to reduce the size of data. So, and this is how it works. Pay attention over here. So what we do is we begin, it's basically a filter, but you can see this one over here is of size 2 by 2. And what it does is out of all the overlapping values of the input, this filter over here, it picks the highest value. It picks the maximum value out of those 4. And it puts that maximum value in the output image over here. And And the stride of this, in a pooling layer, the stride of the filter matches the dimension of the filter, meaning that in the next step, the filter moves, yes, to the right still, but it moves in such a way that it does not overlap with the previous location of the filter. There's no overlap between two between the two filter positions. So the size of the filter is 2 by 2, which means the stride of this filter for in a pooling layer will also be 2. So no overlap between one filter position and the next position. And then it applies, of course, the same function, in this case the max function, to all 4 inputs, and writes that in the second pixel position in the output. And what happens along the horizontal direction also happens along the vertical direction. So the next position of the filter from this position will be this one. It gets us the third value, and then finally we move from this position to the final position over here, and you'll see that the size of the output image is much smaller than what we had for the input. The input image was 4 by 4 in dimension. The output image over here is only 2 by 2. Functions that are typically used in a pool layer are the maximum function, which we call also a max pool layer, an averaging function, which simply averages the values that the filter sees, also called an average pool layer, or a really interesting one that randomly picks one of the overlapping pixels, called a rand or rad pool layer. And like I said, the key purpose of using pooling layers is to make representations, intermediate representations, smaller and more manageable. And by making them smaller, and what do I mean by manageable? By making the representation smaller, we're reducing the number of parameters that have to be trained, of course. So over here, if you have a depth 1 slice of input, apply a 2 by 2 filter with stride 2 to that. It's basically and apply a max pool layer that would give you as output. So the maximum value that you see in here, 6. That's why we see a 6 over here. In the green region, which would be the second position where we put the filter, the max value is 8. That's why we see 8 over here. And we move the filter to this yellow area. The max value over here is 3. That's why you get the 3. And then we move it to the final position. In this blue region, the max value is 4. That's why you get this 4 in the output. And that's how a max pool layer works. And for a significantly larger image of, say, 224 times 224, which, let's say, had enough filters applied to it before that we have a depth. It has a depth of 64. Apply a max pool filter to that, a max pool layer to that. The output from that can be something as small as, actually, if you apply the same 2 by 2 filter to it, the output from that will be 112 times 112, while retaining the depth of 64. In graphical form, one slice, one layer of that input volume, it looks like this. After passing through a max pool layer, it could look like this. reduced in size, and all the smoothness that you see over here in the feature in this feature map, much of that is gone. And uh, uh, although pooling layers work pretty well, uh, uh, Geoffrey Hinton had this to say about their use. So the pooling operation used in convolutional neural networks is a big mistake. And the fact that it works so well is a disaster. If the pools do not overlap, pooling loses valuable information about where things are. We need this information to detect precise relationships between parts of an object. So Hinton's alternative solution to using pooling is something called capsules, which are subnetworks in networks. That's the alternative that he suggested. One last image. So what kinds of features? I talk about features. What kinds of features are we talking about? So uh, here's something from the real world from a 2013 paper by Zieler and Fergus. This is a visualization of the different features uh, that uh, uh, were found in image on ImageNet. So let's say you have, so it begins with low-level features which do not look like much, right? Horizontal lines, vertical lines, different angles. Uh, by the time you get a little deeper into the network, those features start looking like uh, slightly more complex shapes, not just these lines and transitions of colors that we saw previously. And by the time you get to the end, near the output, you can actually see some features. You can actually see something recognizable. So I'm not sure how. So this over here, for example, looks like the rim of a wheel. It's the edge of a car, like the corner. This one looks kind of like a headlight to me. It could be wrong. We have a honeycomb pattern over here. Yeah. So some of these begin to look like something from the real world. And then finally, you have some kind of uh, usually fully connected layers that uh, get you to some kind of classifier. So that's it up to here. And in the remaining part of this chapter, I'll show you some more implementation-specific material for convolutional neural networks, in which we'll also look at some snippets of code that uh, show how you can perform some of these actions and how simple they actually to perform compared to, say, a generic programming language, if you're using the right library, of